Live streaming is on.
Well, that is run circles around them
Yeah.
and draw 3 walks.
Are you sharing or doing anything?
I'm sharing and my camera's on.
It's got a screen with a Mercury lamp backlight.
Say something. Hello. Hello. What? Okay.
And it also looks
Yay.
good.
Actually, let me close the. I may have been carrying that through Jitsi.
Okay. Testing. It's good?
Yeah.
Okay. Hi, everybody. Today I'm going to talk about how my PhD research. This is like close to what I would say for my defense, but it's like for a different audience and like I'm zoomed in on different things. It's going to have 3 parts. First, I'm going to describe the problem of reproducibility. That'll probably take most of the time, or like be the longest section. And then I'm going to talk about the technical solution. And then I'm going to talk about extensions of that solution. This I had to, since I was like wrapping this up 5 minutes before, I have the least amount of stuff there, and the most amount of stuff there. Yeah, and the roadmap is down here too. So yeah. And I'll pause for questions at certain points. That would be like the best time to ask questions would be like after that. So yeah, okay. So science. It is one of the properties of science in order to work is that it has to be collaborative because you need to validate other people's work and often you're building off of other people's work. Like this picture, do we know what this picture is? Yeah, and this guy refuses to look through his telescope because if he did, he would see mountains on the moon, which is not consistent with Aristotelian physics. So he says, I will not look through this instrument because, and so this is like the point of science though, is that in order to actually participate, you have to reproduce other people's work, copy other people's experiments, to just see if they're right, and also to extend them. Even Newton himself, like his theory of light, completely shattered by the single slit refraction or diffraction. But when that experiment came out, he actually repeated the same experiment and actually noticed not only that it was correct and it broke his theory of light being like a bunch of tiny bullets, but that he was the one who observed these kind of rainbow fringes on the end that would later on help us figure out the nature of light. So science has always been collaborative from the beginning. And yet there's a replication crisis. If you may have heard of that term, it's a trendy topic to talk about how nothing is reproducible. Why might that be? Adi and then Jenna. Yeah, well, and I haven't even said computers yet. So just in general, maybe the experimental conditions are different somehow. Jenna?
Funding, it's not glamorous for people.
Yeah.
Confirm that it actually does hold up.
Yeah. So I would say like difficulty in reproducing the same conditions and that it's expensive and there's low reward. There might be people committing fraud too. I mean, I don't really know. They're like the publisher perish pressure and kind of stuff like that. So things might get published that are not true. And even if everything is completely fine, even if all of these things were completely erased, statistics would still be a problem, which is that if you're setting your p-value to 0.05, that means there's a 1 in 20 chance that you would observe the data with the null hypothesis. That means if you do 20 experiments, probably one of them that is statistically significant with p less than 0.05 is spurious. If you did 20, there are way more than 20 experiments. So there are going to be some spurious experiments, actually quite a few spurious correlations that get reported and published on. And then there's the publication bias. So people are more likely to publish the positive and the negative results. And I can't really attack the statistics you have to live with because there's some just natural you're trying to determine statistically if something is noisy or if it's actually a true correlation is kind of impossible to do with 100% accuracy. And expensive. I hope to work. Maybe someday I'll be an NSF grant admin, but right now I can't change anything about that. I can't change anything about human nature. But I think that in this problem, you can address how easy it is to reproduce people's experiments. And digital computers, since like the primary like advantage of digital versus analog computers is that they're robust to noise. Like a bit is either 0 or 1, and there's no like having to read a needle or having to steady your hand to get it to be a certain value. You like type in the value, and then it's that value. And since it's digitized, it's robust to these like small errors, like when you're typing something not exactly the same way. That doesn't matter because it's digitized. So it should be much easier to replicate other people's experiments, which will address the difficulty reason. But is it in practice, or like why might that not be true in practice?
People don't care about reproducibility in the first place.
Yeah, that is one. I think when people were asked about it, why don't you share code? I think that not caring is true, but you have to look at it like a cost benefit. Like they probably care a minuscule amount, and it probably costs much greater than that. So it's not that exactly they don't care at all. It's that the cost is much greater than the amount that they care. Is how I would say that. And
They're not like incentivized.
yeah, they're not incentivized, and I can't change the incentives, but I can change the cost. So there's this study, Kohlberg and Probsting in 2015, highly suggests you read this because they actually just asked a bunch of people for their code, randomly cold emailed a bunch of people, and then like published the results, which is kind of badass. So like 43% of the respondents didn't give him their code. He's like, please give me your code. I want to reproduce your experiment. And 43% said no, because many of them were unsure of the right version. Okay. And there were some others that so I'll read you exactly their quotes, which were too long to put on the slides. I'm just hoping that this is a stable working version of the code that matches the implementation we actually use for the paper, but I'm not really sure. I'm not very sure whether this is the final version of our code used in the paper, but it should be close. Another kind of thing that came up is lack of documentation. This is pretty common. There was only one for the paper. For the paper, we used a prototype that included many moving pieces that only one student knew how to operate. They did not have time to integrate it before they left. The result will require a lot of hand-holding to be able to use. Even our own students find it unusable. I don't have the bandwidth to help anyone come up to speed on this stuff. It was like a lot of things that people said. Do you have a question about that?
I guess it's just like, I don't like publish, I don't have questions, but like during the peer review process, do you want like request code? Like,
No.
some journals.
Yeah.
Is it machine learning?
Machine learning is a bit more, yeah. Well, actually, it depends on the ML journal. Some of them have better practices around this. They might give you an extra badge if you do. They might ask for it, and it's optional, and you get an extra cookie if you do. But yeah, yes. As someone who's researched in systems before will tell you. Yeah. Yeah.
In my field, it's awful. Like atmospheric science, people will build their own little proprietary things and then not release it to anybody, and like unintentionally, they don't even pretend to be, to be open about it.
I think that if you,
they call it their IP. Like
Yeah.
even my advisor has said that.
I think that if you, there like many people will be like that, but I think that if there's like 1% of people who it's like too costly that I can like help, I think that's worth it for the 1%.
I think more, especially ML is much better about doing more open research and not worried about the IP question. I think it's just other industries and maybe not working. In that case, but steel and thunder, I'm sure the filter thing is actually far more common. So you'll see code, but like,
Yeah, unable to acquire the software firmware. A large part of our code depends on code from other tools from these ancient versions. It will require a huge amount of effort. So they're not sharing their code because according to their statements, we are kind of taking it at face value. But according to their statements, they're not sharing their code because of these. Some of them are not sharing their code because of these like technical things. There are costs associated with sharing your code. There are other responses I didn't include that were like the licensing, like if your code is proprietary, you developed it for a company or something. There are also, even if you do share the code, there are still kind of ways that it can fail due to like build errors. 27% of the time that they had the code, they were unable to build it. The researchers in Kohlberg et al. Were unable to build the code that they had, even though it was published. Because often the distribution is missing files, which is a bit of a user error. Incomplete documentation and missing third-party packages, which is also a user error.
What's the threshold for deviation here? Like, do they just follow the README exactly and then give up if there is a single mistake?
They put two, the methodologies, they put two research assistants to build it with 30 minutes different times, and they would and if they still couldn't build it after that, then this is what was reported. So it's like you also got to consider maybe it's possible to build, but it's not easy. That should kind of count as no, kind of, because it's not accessible to many people. If only like 5 people in the world could build it, it's not really accessible and reproducible.
The classic one is like it builds only on that graph.
Oh, yeah. Yeah.
Yeah, I've definitely seen secondhand, thankfully, researchers or come into the like Ingrid asking for help where it's like, okay, you have a specific version of this software stack running on Ubuntu 18, and you're using dependencies that haven't been updated in half a decade. And if we touch any of this, it's all going to explode.
And yeah,
And
often
they're
Python
like, can you
2.
help me get this to a new enough version? I'm being told I need to upgrade. It's like,
Yeah.
no, I can't.
There's another study called Why Workflows Break. A workflow is like a programming language. It's like Make, where you're structuring just the glue code that connects other programs together, other scripts together, and it's like at a higher level glue code, and that's what we're talking about. That kind of is supposed to help theoretically. That should make it much easier to make stuff be reproducible, because you can put each part in its own little node and only rerun the part that you need. And if somebody else needs to reproduce it, they'll rerun the whole graph. It should make things somewhat easier. But there are still a huge number of failures caused by third-party resources, insufficient metadata, unavailable data, and insufficient description of the execution environment. Then I did a study. So this one was 2012. So I did one in 2023 that's on a different corpus, but asking similar questions of workflows. And 32% of the ones that were unbuildable were due to missing inputs, and 11% were due to the Conda environment not being solvable. I also looked at how stale they were. So when the ones that succeed, they would be like kind of like a 1 at however long it's been since they were published. And if they fail, they're kind of like a 0 at that time. And this curve is kind of like an aggregate of all of those points, which tells you kind of the probability, if you're a certain number of days after publication, that the workflow is still alive. The red curve is the average of both groups. And it says that after about the half-life is where this intersects point, the probability of survival is 0.5, is about 2 years. So it's that every 2 years, there's like the probability that you'll still be able to build it goes down by half. So that is, I'm drawing on studies that are more than 2 years old. Where'd I go? So I'm drawing on a 2015 and a 2012 study. Imagine if I couldn't access or utilize those results. My study is more than 2 years old now. Imagine if not being able to use those results. If imagine Newton not being able to reproduce the double slit experiment in his own lab. So what about Docker? Well, somebody studied this like a notebook binder hub where people put all of their notebooks, and 56% of the Docker files or the Docker images did not contain a lock file. So if you're using Docker for reproducibility, you either have to store the image or you have to rebuild the image from the Docker file. If you store the image, that's expensive. This public notebook service was end up costing like $1,000 per month. If you try to rebuild it, then it's not reproducible anymore because 56% of the containers don't have a lock file. And this is showing you when they don't have a lock file, how long will it take for them to get stale? And this graph is showing you that. So this says that after 10 days, that's approximately the half-life for both of these groups. For an underspecified container, which means there's a container, it has a Docker file, but everything is not locked down. After about 10 days, it's going to be pulling in different software versions than it was previously when you rebuild it. So it's not actually reproducible. If you have to rebuild the image from the Docker file, you need to use something else that makes it be reproducible. Yeah.
I was under the impression that for stuff like Docker, even if you pin it to a specific version, oftentimes like versions just like of like Docker based images, specifically other images are built off of, will just get like cheated out.
Ubuntu images that are older than 2014 are hard to, they disappear. Yeah.
So I mean, 2014, that's over a decade. That would be a significant improvement.
Yeah.
But still, like even with a lot.
Yeah, and the tags are mutable. So if you're from Ubuntu 16.04, that's mutable.
That's the mutable tag is the biggest problem.
Oh, so behind the scenes, they can change what is Ubuntu 16.4.
Yeah.
So it's not locked to like a hash.
Yeah.
I'll say like this is the tag.
It's like a git tag. It's completely analogous to a git tag. And
you get tagged. Not a
Yeah.
tag.
Yeah,
Okay.
you can use the hash for Git commits and for Docker. And if you want strong reproducibility, you should consider that. But then also you have to worry that hash may not be findable some point in the future. Because you can't store it indefinitely. Yeah.
Like if you build
But
your
then
own
at that
container
point, you
registry,
should store the entire
Yeah.
Yeah.
Then you're kind of like in a
binary storing process.
Yeah.
So,
This paper outlines more of the costs too. So
did that paper talk about the tag moving from?
no, I think that because they're talking about a service called Binder Hub, I think that in that,
That guess is probably like
yeah,
a more controlled.
Yeah. So this paper is very interesting if you want to learn more.
I think like it would be helpful for the role of like teaching people what an underspecified container.
Yeah.
Is. Like whenever you talk to the degree school problem, like people are like, oh, Docker collector.
Yeah.
No.
Probably a bunch of those people didn't even know what a lock file was.
Yeah.
I don't know, that'd be like a helpful like public resource.
Yeah.
What is this plotting to? Like container failure probability?
This is the number of containers within each subgroup that when you rebuild them at the time t days after they're published, get different dependencies because they're underspecified than when you built them at time 0. Although the y-intercept is kind of suspicious there. So this says that after 10 days, there's like a half chance that you're getting different dependencies.
So to clarify, that does break reproducibility in a totally pure sense. It doesn't necessarily mean that it doesn't work.
That's true. Yeah. Yeah. And yeah, if you get different results and the environment was different, you have to investigate, was it because the environment was different? Is it because the code is non-deterministic? Or is it because and if it's not deterministic, is that like intentional or unintentional?
Why do you think the Conda one is more volatile?
I think that is because Conda includes more packages than pip, because pip kind of assumes that your C compiler is already, it uses the C compiler on your system, whereas Conda, the environment will include a C compiler if you're, for example, installing something that needs the compile C extensions.
Was it maybe that they didn't even check for the system, for the pit line, they didn't even check the system itself? I don't know, we don't have to.
That's plausible, yeah.
I would guess what might be the difference is that if you're talking about like the bunches container, if pips using the underlying system dependencies, those are gonna move as blocks, basically, like you're
Yeah.
not gonna have any system changes until a bunch of stuff changes in your like underlying OS containerated changes.
And by that time, you
Honda is
yeah.
more like, until like, it's, I think it might be the version release versus the release.
yeah, that is possible. So all of this stuff, when I talk about this to my computer science department professors, it's like user error, right? Like, oh, they should use lock files. I never have this problem because I do this. I use that. I use Nix. This is not a problem for me. I have good hygiene. I have good documentation, so anybody can figure it out, and all of this stuff. And it is user error, but I think that we have a responsibility to design systems that are harder to misuse than they currently are. We have to think about designing systems, the people in this room that know a lot about Linux, designing systems, or about operating systems rather, designing systems for people who are not in this room to know how to use easily without studying computer science for 4-year undergraduate degree. A lot of scientists learned how to code on the job. They studied biology and chemistry and learned how to code on the job. And so we need to like make a system that works for them. And it's hard. It's a hard sell within computer science because these errors seem preventable and like the user's fault. And if they just did this, that would be better. But I am going to take a stab at designing something that will help them without them having to know about it at all. Yes.
Just to give everyone like a perspective, like because I do like bioinformatics related stuff, a lot of the bioinformatics teams will contain one person that knows how to code, and then a bunch of people that know basically nothing about computers. Period. I entered at a hospital and I was the only computer literate person outside of the IT person in the entire research department.
So I think that sets up the problem. It is about reproducibility, but it's mostly about usability. Now I'm going to talk about a technical way to improve that. It's also like, if this is a social problem, like, isn't that a social problem? And it is a social problem, but there are things that you can do technically that address social problems. Adi? It's a good question. So smattering of both. So Kohlberg and Rebsting at the very first one is computer science, but Zhang et al. Why do workflows break is more general and is like computational science. And what was the other one? Oh yeah, the Jupyter Notebook one, that's the binder hub containers one, is definitely more like non-computer. It's not specifically computers. And mine was on workflows, snake-make workflows, which is actually mostly bio people. So yeah, smattering of everything. So the user interface that I'm thinking of is record replay. Like somehow you click a button on your computer and it starts recording what you do. And then at the end of the day, when you're trying to publish, you say, tell me how I made that file. And right now you have to bookkeep that. You have to bookkeep what files you need and what versions of the code that you used in that one. All those emails are saying like, oh, I think this is the version that I used for the paper, but I don't really know because it's constantly changing. It has to be bookkept by you. And even if you're using Git, well, now you have to remember to use Git. You have to remember to make a tag. So I argue that whenever you need human effort, some people are not going to do it, and some people are going to make errors, make mistakes, and incorrectly do something. So you should try to make something that requires as little intervention as possible from the user. And if it's bookkeeping, I think that bookkeeping is exactly what we should be offloading to computers because they're good at it. Human mind is terrible at bookkeeping. So what I want to do is with record replay, bookkeep how you got to this file. So once you're ready to send that file to a publisher, include it in a paper, you can say, how do I get this file? And give me a thing that I can send to somebody else that they can run to get that same file. That's the interface that I'm looking for. And it could be a button in RStudio, because a lot of these people live in RStudio. They would do their taxes in RStudio if they could. That is kind of the interface right now. And it also needs to not be just for Linux. But right now I'm doing a research prototype that does not have that interface yet, and it is just for Linux yet. And then once I prove this out, then I can talk about making it a more beautiful solution. What should we record? That's an open question for everybody.
Pip list, dump to file.
Okay, so you're saying like if they're using pip, dump this, do this command, dump it to the file. Yes, that is a good idea. All build dependencies.
Yeah.
How do you know what's a build dependency like? Those are both good ideas. They're both specific tools that you need to like, oh, they're using this. They're using make. Now I know to get the make dependencies. They're using pip. Now I know to get the pip list. Jenna?
We get the dependencies by, and I'll admit this might not be as well effort as you want, but do like a transparent file. Now, obviously, that's a Linux specific example, but the idea of like, have it running in a direct, prefix it runs in an environment where it sees everything in the file system, but as soon as it actually tries to touch something before it gets to a note of that's made, like it needs the file.
That is one way. I think that to generalize your idea is to record the file reads and writes.
More the file touches, like.
Yeah. Well, okay.
Well, but like I guess like file touches are going to include.
Yeah.
But not necessarily like every file touch, just the first one.
I mean, it's going to be pedantic, but like I guess like with Linux, I'm going to record every instruction in right?
I think that we can discuss that more later. I think important thing to note is that if you record the file reads, that kind of takes all the scripts that you need, all the data that you're using, all of the executables that you're calling, all of the libraries that they need to run, and even calls to dev random that are going to like seed your randomness, all kind of get captured. They're all the same thing because they're all files, and they all, if you just record those, you got all of these bases covered, which is not all of the bases that exist, but it's quite a few. Adi? Well, scripts are still files, data is still files, executables and libraries are still files. Random is maybe not a file. I don't actually know how that works.
They also, I mean, the flip side of that is though, like, dev random is very rarely used by that class.
I think that they might actually get, you don't notice that they get used, but I think like when NumPy starts up, I think that it's going to seed itself with something from dev random.
It just sees itself. I haven't checked, but
I'd be willing to bet that a lot looking for using dev random.
And you don't notice it because you're not typing open dev random, but it's in a library somewhere.
Yeah, sure. I mean, I know that like a lot of stuff, maybe stuff is migrating away from this. Uses the CRAN function.
Or time null, right? SRAN.
So yeah, well, how you seed the C pseudorandom number generator is a
Right.
different question.
And if that I think will sometimes come from dev random, sometimes will come from the current time, which you could also say we should record. We should add it to the list.
I was actually going to, go ahead and recall. I was wondering what I use sandboxing in the recording. Are they allowed to make network calls?
Yeah, that's a good question. So we noticed that a lot of them do fail due to network resources changing or not being available. But you like if they actually need the network call to do their thing, like sometimes their experiment uses an API. Like you can't. It's too limiting to prevent that, and you can't. So network calls probably currently no. And I hope to someday do the HTTP gets, because HTTP get is basically like a file read over the network. But hosts, you don't know. That could be non-idempotent. That could be some behavior. And non-HTTP is very, you shouldn't be.
The idea there would be like you cache the network call result.
Yeah, and replay it.
You can replay that.
For HTTP gets, that seems like a great idea. For everything else, that seems super dangerous, and it might give unintended results.
HTTP get is also not
It's not necessarily idempotent, but there's a strong convention that it be. Yeah, because you remember in 1999, those like counters every time the website gets gotten, but there's a strong convention that even though it's not going to be idempotent, it's going to return a result that would be plausible. That's like doesn't break any assumptions that the program had, which means it gets a stale count, but that doesn't break any assumptions.
Why would you not save the results of the network call?
I am saying to save the result. Yeah, so you can replay
in
that.
that case, gas calls return different values every time you issue because you save the result.
Well, in Thin1 program, you save those results, but when you replay it tomorrow, if you're going to feed it back the results it got today, and if it's expecting Git to like get you the current weather, it's going to do the weather from the wrong day. Yeah. But I think that there's something, it's like a imperfect but still good thing to do. What about the parallel schedule? So, and GPU, this matters a lot more. I think that's too hard to record right now and to replay right now with user level tools, not the kernel. Especially on GPU, just the data from the schedule is kind of big. It's hard to control from user land anyway.
Yeah, at the GPU level.
Yeah. So what does this mean? There's kind of reproducibility. If you think back to those problems we're solving, none of them, those emails, none of them were like, oh, the GPU schedule might be different for you. The main concern that they were having was, oh, I can't even run your code. So I don't even care if the GPU schedule is different because I'm stuck on step before that, like underneath that. So I'm solving that problem that's like more fundamental. And then once you get their code to run, maybe you're not going to get the same result. Maybe the scheduling is going to be not deterministic. But at least you can run their code. And that's the improvement that I'm trying to make. How we record this. So Jenna kind of already suggested one, which is fuse. And this is good for file reads. You don't exactly get the forks and execs here. Yeah, so you would want to combine it with something else, and maybe that'll inspire somebody. Adi, you're inspired? Say again. Okay, library interposition. You could use strace uses a system call called ptrace, so I call it ptrace. Ptrace is like how everything you would need to implement strace. A system call, and yes,
I don't know what it's actually built on top of.
it uses a combo of these two. Yeah.
You could dynamically
Okay.
disassemble and reassemble code to replace syscalls with a jump to a record routine. Then
Yep. Dynamic binary instrumentation. Yep. Yes. I'm glad you mentioned. EB. What does that stand for?
I thought it was extended Berkeley.
Either way, it's a Berkeley packet filter that's like a little bit plus.
It's the Berkeley packet filter plus plus.
Yeah. And basically the kernel. So, and since you two brought it up, how does that work? That's okay.
How does UTF work?
Yes.
Actually, I mean, it is what CrowdStrike is implemented on, and it is very similar in concept to what caused the famous CrowdStrike vulnerability. It effectively provides, I don't remember the exact semantic details, but it effectively provides a way to dynamically interpret byte code in the
Yeah.
kernel.
Yes, but there are pretty specific limitations. In particular, you can only read things in eBPF. You can't change the output of a syscall from eBPF. You can intercept it and you can see what it was. You can log it. And if we're going to actually do this, it might be nice. For example, if you read a file, we might want to stat the file too. But in eBPF, you cannot issue a new system call. If you're currently intercepting a read, you can't somehow issue a stat. You can only kind of do things that the kernel has exposed through certain hook points.
Is there not a way for you to hook like the end of
You can hook the end, but you can't do whatever you want, and you can't issue a new system call. If you're doing a file read, it might be nice to also do a stat. Stat tells you the file time, mod time.
If you're doing a read and presumably you got the file descriptor.
You have the file descriptor.
Is there any way you just, instead of statting the file, just look around in the kernel data structure and find it?
You can't explicitly call other people within the UIUC update, but you can populate that somewhere else.
That's true.
Another program to pick up.
Yeah, but you can't issue a new thing de novo somehow. And especially if you need it to happen, synchronously, like before you finish this open, you need to stat it to make sure you know what it is. You can't do that synchronously.
My question is, why do you need static information?
Well,
Not
okay,
just
okay.
like, you're already in kernel space. aren't
It's
you? That
possible
information
there's a way to get it.
around.
It's possible there's a way to get it from the kernel without doing a system call from the kernel memory. But I'll give you a different example. Sometimes if you're doing an open, we need to do a copy because you're doing a truncating, overriding open of something you read previously. If you're doing a truncating open, then you need to copy that so that when we replay it, we can feed you back the original version. So you need to issue a copy when there's an open sometimes. And that is like really not possible to do in EPUB. You really can't like.
If you had a, I mean, I agree, but you can't directly get that by, so you can't do system calls. Could you say populate a character device?
You could do something like what Rishi said, where you have a companion program.
That's what I was thinking, where you're like, okay, something's happening on this file descriptor of this PID. You get out of the character device at a user line process that then going to go look in prompt.
So there are some extensions to the UBPF, like you can actually write a schedule now in UBPF. There's like SCADA, it's like SCAD extension or SCAD.
There's some extensions.
Yeah, it's SCADX, which basically lets you can basically hijack the content scheduler and build like a UBPF schedule or whatever you do.
You can do a lot of stuff.
So I'd be curious like what they're doing because that's like
Yeah.
kind of a modification to it's not syscall level modification, it's some other level modification, and I wonder if that would be like
Yeah.
you could build it yourself a recording facility.
You still have this other problem, which is that when you're using ptrace, library interposition, or fuse, or whatever, all of your user permissions are going to get tested by the kernel to make sure you're legally allowed to do that. But if you're doing eBPF, you can spy on everybody. Like, since you're in the kernel, the access check already happened.
Yeah.
That
You either need to do the access check yourself.
you're right. Coding and independent permissions checking stack in eBPF, right?
Yeah, maybe let's not do that.
Yeah.
That sounds like a CVE way.
And then the other one is to hack the kernel. And both of these, this is the most dangerous, but some of the danger here also applies here, which is that you kind of have to be, you're opening an attack surface. Both of these open, this one's a huge attack surface. This one's just a regular attack surface. Dynamic binary instrumentation is possible. It slows you down because you have to potentially like insert and destroy. x86 is really hard to insert.
It doesn't have static instruction.
Because the syscall is bigger than a call is bigger than a syscall.
Yeah, because it doesn't have fixed instruction.
In other architectures, you can do it's easier because you can replace the syscall with a call to yourself and then do the syscall or whatever. But in x86, the size is the other way around.
Yes, it means you need to resolve. I thought about this for a lot, and I think you need to resolve all of your offsets back into symbols.
It's no fun.
That you can shift them to fit in additional bytes, at least at a per segment level. In theory, if you do this before it gets mapped into memory, you don't need to do it.
There's a lot of complexity there. Fuse, it gets your file opens. It doesn't get your forks and execs. So I'm kind of left with these two, and this ptrace has been tried the most. So I think we got everything I was thinking of. Oh yeah, and there's a nice example of this that we talked about because I was like figuring this stuff out like concurrently to like doing glug meetings. So we kind of talked about how this works in Linux. So this one is like you pretend to be libc. So it's like instead of fopen, they call your fopen, and then you do something else. Like log that call and do the real fopen. So I tested some existing stuff. These are the different tools on the row that I tested, and this is the method by which they use. So all of them use ptrace because I eliminated these. Dynamic binary and fuse, it's hard to come by. So the most of the work has been on ptrace. This is a performance impact. 0 on top of something. 0 is native, and it's a percent. So this is 4% overhead. And you can just tell that the ptrace is too slow. The reason that it's too slow is because in ptrace, you have 2 context switches. You go from the tracee to the kernel. The kernel says, oh, you were being ptraced, debugged. So whenever I got a syscall for you, I'm supposed to ask this other person first. So then it goes and asks that other process. Another process will log that you're trying to open foobar, and I'll use the pointer, and it will return. It says, yes, they're like, I'm not going to modify it, or I'm going to modify it, and then the kernel will actually do the system call. But in the library interposition trace, the tracer kind of lives within the process space of the tracee. That means you're the guest. The tracer is the guest, and it has to like not mess with too much of the tracee stuff. It's, for example, if the tracee wants to open a file descriptor and it kind of like knows that it's going to be file descriptor number 5, the tracer can't really mess with that too much because it can't open a file because that would like disrupt the file descriptor assumptions. It is, and there are lots of software that does it. Java, the open source implementation, so ICT, iterates through /proc/self/fds, and just whenever you make a sub-process, it iterates through this directory and just closes all the files it sees, which could be some of the tracer's files. And this effed me up because I'm trying to do library interposition, and I didn't know that they were going to do that. So yeah, so tracees will do this, all kinds of stuff that could mess with the tracer if you're living in their house, in their process space. So you have to be careful. That's something I learned. So prior tools are not feasible. Kernel and eBPF, they're not feasible because of the attack surface, or they're too slow, like ptrace. But library interposition is a promising route because it skips that context switch. From the graph, it looks, this is not doing as much work, so it's not a perfect estimate, but it looks like the overhead is much lower. This is just logging the names of the files that get opened. So it's like really doing like a very small amounts of work. But so is strace. Strace is also logging the names of the files that get opened. And so the overhead of ptrace is going to be like kind of at least the overhead of strace, whereas the overhead of a library interposition solution is at least the overhead of FSA trace. Adi? Measurement error. Yeah. So, yeah, I made something called Probe. It stands for Provenance for Replay Observation Engine. Provenance means like is an answer to the question, how did something come to be the way that it is? That's what that word means. So it's for replay though. ChatGPT did me a solid helping me find a good acronym that incorporates all the terms I wanted into something. And probe is like a nice name for something that does this sort of thing. That's it. That's a typo. To be probe. So probe record command runs this command with a bunch of environment variables, including LD preload being set. Well, there's one other that you need to maintain context. Yeah. So because this is a different process, the only way to pass data is through environment variables. It's a completely different process. Well, if you pass one environment variable, you can put all of your other global data into a directory, into a file, and that can get parsed out. So I passed one environment variable that points to like a file that's for everything being pro-recorded, and that's all the common data that you need to share. And then they'll read that, and then they'll find other stuff elsewhere. Yeah. Okay. So this runs the command with library interposition, which interposes relevant functions. So basically like intercepts them. So I'm going to kill Mako. I think that's what's giving me those notifications. What software is that? Mako or Dunst? Yeah.
Yeah, I mean, what's.
Okay, that was Dunst.
Specific one is AD Connect, so most of the notifications we see from.
That was Dunst, though. I think that is dead now. Okay, on the first call, in any thread of any process that's being probed, notice that these environment variables will kind of like transparently work on all of the child processes. Like I don't have to do anything; they're already there. So any of these processes that are children, any of their threads, the first time they do one of these calls, like fopen, we initialize, which means we create a thread local memory mapped log, which is a lot of M's in a row. Never kind of noticed that, but so it can be written to very quickly without causing the program very much overhead at all. So on subsequent calls, we're just going to append a record that call, such as fopen, is happening to that memory map log. And we don't need to like flush it or anything because there are a couple of assumptions, but it's memory maps. The kernel makes sure that page hits the disk eventually. The only like assumption that breaks that is if you take like a power off event. And it's possible that there are other assumptions that break it, but it ends up not mattering because the original code it's kind of assumed that it succeeds, or like it gets to a finishing event. Like it doesn't get interrupted. Like it doesn't get signaled.
I've read for this system call, and if the progress exits for calling in sync and there's dirty changes happening synchronized, it is not guaranteed to actually.
I see. Okay, so my new statement.
PR for you and that to fix that at some point.
Okay. My amended statement is that if the original thing that you're trying to run gets to an exit, like either it doesn't even matter if it exits with failure or exits with success, but if it gets to an exit,
yes,
then the probed data will make it to the disk. And we're trying to record something. It's assumed we're trying to replace something. It's assumed that the thing we're recording kind of like works to some extent. There's a demo that I'm not going to do because I don't have enough time. But you can click this link in the slides that we're going to publish. There's some stuff that I learned, like that just because libc says fopen exists doesn't actually mean that fopen is a symbol, because it can be renamed in a header, like __ fopen. And there's like the 64-bit and the 32-bit variants, and those can get renamed. It could get macroed, yeah. I also have been using a Nix environment for this whole thing for the dev shell. And a lot of people who are, Jenna and I know Nix, but we worked with 2 or 3 people who don't. And it just kind of works. Like they need to copy paste something to install it. And then they need to enable the dir env. And then as soon as you cd to the project, now all of a sudden we're using an old GCC with an old glibc with an old, like everything is very customized and very specific, and it just kind of works, which is magic.
Yeah, I'm just curious, like which installer you're using.
I think it's Determinate, because they enable flakes.
Yeah, I would recommend using Determinate.
Yes. Yeah. A crucial mathematical aspect of this is that a single node, if you're doing this thread local logging, feels like a distributed system, because with ptrace, everybody has to go to the tracer before they get completed, which means there's this global bottleneck or serialization point. The kernel, that's true. With eBPF, that's true. But with thread local memory mapped, each thread has got its own memory mapped file that it's logging to. There's no serialization point. So you don't know which thing happens first. So it starts to feel like a distributed system. And where like these certain events like synchronization that we're going to be recording in our log, order events between this thread, the caller, and some other threads log. So it ends up becoming a distributed system. We'll define a happens before ordering, which is the we've discussed in that meeting where we talked about crash consistency. It's the transitive closure of synchronization order and thread order. So it's like a combination of those. Race conditions are actually quite common in this formulation. Anytime you have a shell pipeline, you have true concurrency in this sense, because A, B, C, and D, E, F are actually running at the same time, and they're both accessing the pipe at the same time. The pipe is a file, right? It can be implemented as a FIFO or as an anonymous pipe, and they're being read to and written to at the same time, which means there's actually like concurrency right there. So we have to grapple with that. And so I kind of defined a new like binary relation called information may flow, where information may flow from A to B if A is a write and B is a read, and B does not happen before A. And while lots of people have studied the happens before graph, I'm trying to find better algorithms that produce this information may flow graph, which is actually what is useful, because that graph is actually what tells you like, oh, this file is derived from these processes, which are derived from these files. So if you want to reproduce this file, you better archive these. That's what that graph is helpful for. And that covers the technical solution. Any questions about the technical solution? Oh, yes. Yeah. So because we want to make as low overhead as possible, by Jenna, this is actually something that Jenna worked on.
I was to say, yeah, I'm like trying to keep my mouth mostly shut, but like lots of this is like code I wrote.
Yeah.
So it's kind of cool to see like the culmination, but I can see it immediately too.
Good luck. So in order to make it low overhead, we just dump bytes from a C struct from memory into and we mem copy them into the mem mapped region. So we don't do any serialization at all when the program is like in the critical path. There's no serialization. Well, so right after the program is done, then we're going to turn that C struct, which is very brittle and it is like super annoying to work with because it has pointers that are not correct because of the memory map. Yeah, it's not on the critical path. It can happen right after the program is done. It can happen overnight while you're sleeping. But yeah, we transcode that and put it into actual serialization format, and ideally into a database. Actually, ideally we just go straight to a database.
What's serialization?
Right now we're using JSON lines, which actually does not have a bytes type. For JSON, you have to make it be an array of integers, and all of the paths at the C level are, yeah, they're just numbers, an array of numbers. That's what I meant. At the C level, all of the paths are bytes. They're not necessarily UTF-8. You cannot, if someone opens a file, you can't assume the name of that file is UTF-8. So, yeah, right. Well, I mean, they might have changed the locale. I mean, but in the POSIX says that you can do anything except for slash and null byte. Any other character from 0 to 255, I mean, except for 0 and the slash, is allowed in a file name. No, you can use 128, 129, and above. Some programs.
It's not even a Unicode. You can not even have a valid, Unicode code.
Yeah, that's right. There's more than two. You have more than two.
Okay.
What is with the Unicode?
No, so it's a chart. And think about, put yourself in the shoes of Kernighan. It's 1975. So you're writing char star, and when you type in char star, that can be any number from 0 to 285, any integer. So it's not UTF-8. It's any ASCII, and it's even except for two specific. Yeah.
And then so it's just like those. So it's like in the office, like used directly like that. It's not like actually very good. I think Unicode converts to like multiple ways. Yeah, but like the Unicode thing is like it becomes assumed on things to do like the
Yeah, the kernel just sees char star, and probe just sees char star. And then when we serialize it, we have to serialize it as an array of numbers because of that.
Why do something?
Mistakes were made. I don't know. No, because in the long run, it's going to go straight to a database, right? I said that a little bit earlier. So in the long run, we're going straight to a database. We're not even going to have serialization. It's just going to go to a SQLite database. So then it's not going to matter. So this is really just a temporary thing. Yeah. And then, okay, so Rust and C++ both have a language runtime. I think that in both cases, they're kind of needed to fire the constructors and the destructors of static variables, static global variables, even if you don't have any. And I think the STL does have some, actually.
Some like core overhead.
I don't know. Yeah, so no-stood Rust. Another problem I encountered with Rust is that in C, we have variadic functions. Just open is, is it Crete or open that's variadic?
Yeah, you don't have that in Rust.
You don't have that in Rust. So you can't interpose it.
Header.
Yeah.
And
And
if you like a C header, then like type,
it's super
it's, like, not
gross.
worth it.
Yeah, it's super gross because, and I hate variadic functions, but whoever in 1975 didn't know that that was a bad idea. That is a function. Let's look at a man page real quick.
Oh, like exec algorithm.
Yeah, like execl.
You just have like a pointer, like, all the original thing.
Like exec.
Yeah, execl is another example of variadic.
Good one. Yeah.
Printf is another example. So this can either have, see the ... That means it either has two or more, and somehow even this can have more, which is not true. This,
That's not important.
you can't do that. And execl is, you're right, is another example. Well, I'm trying to interpose this stuff. They might call this. I can't prevent them from calling this, and I need to know if they do. So I need to interpose it. So I need to implement something with the same signature. If the signature is different, they'll like get fucked up.
My question was like on the Rust point, and really, if you wanted to go and you could implement Pro in Rust, but you have to like how bake this periodic layer in some ugly way.
Yeah. So let's see how many slides. Oh, just one slide left. There are plenty of things you could do with this. I think a good research idea needs to have legs. One is that it kind of gives you incremental computation like make, but you don't have to declare your dependencies. They're observed rather than reported. And if you ever typed make clean, it's because your make file is incomplete, or you're like there's a mistake somewhere. Because if make actually worked correctly and your dependency was accurate, you would never need to clean. But the fact that you do implies that observed is better than reported, because reported is always incomplete. So you can do stage data analysis. If you want to like change somebody's plots in a figure, you could just like, if they uploaded this graph, you could just really easily change a line and only re-execute the parts that actually need to get re-executed. And I'll just do this next one, which is that if you're, instead of dropping like a pile of scripts, if you repose a pile of scripts, just run it once with probe and turn the graph that it found all of the dependencies into a workflow. And now it's like solves the documentation problem to an extent. So now you know like what's happening to my data. Oh, it's this filter and that filter. And that is also compliance tracking. Like you have to make sure that this result doesn't come from any race or PII information. So that would be how that works. So that clock is 2 minutes fast. So I'm only 3 minutes over. So, and that is where I'll end it.